Okay, so this is an investment problem. It's saying if you invest $4,000 in a savings account, 8%, compounded quarterly, how much do we have after 7 years? Now, we looked at this last week, and the formula we gave was the future value. We're going to just put S as the symbol that the book seems to use for future value. P is for present value or principal. 1 plus R. And some people put N in here, some people put K, it doesn't matter. All that is the number of periods per year to the power of N or K times T, where T is your number of years. So in this problem, P is the $4,000 that you started with. 1 plus R is 8%, so that's 0.08. Divided by K, it's quarterly, so that means how many times a year? 4. So to the power of 4 times 7. So this is going to be 28 here. So in the calculator, you just punch in 4,000 times, parentheses, 1 plus 0.08 divided by 4, close the parentheses, power of, you can put 4 times 7 there, but it's easier to just put 28. You get 69, 64, 10. Just come anywhere close to that? So did you try to do it one cycle at a time, or did you try to do the formula? Okay. On a quiz, I would give you that formula. On a test, I might not. So just so you're aware, but as long as you save your quizzes, it'll be there. Other things we discussed on Thursday. We discussed half-life. Half-life, the amount of product that is still there, we'll call that little a, is equal to the initial amount, A0, that's, or A naught, A0 means the initial amount, at time 0 is what that stands for, times 2 to the power of negative time over half-life. Now, if you're taking a quiz or a test, be very careful. It's really easy to miss that negative up front because it kind of blends in with the fraction bar. But make sure it is negative because this is decreasing. The other way you could do it is you can make this a 1/2 instead of a 2 and make it a positive power. But usually you see it as 2 to the negative power. So let's say that we start with 500 milligrams of material with a 7-year half-life. How much is left after 20 years? So same type of thing. Plug into this formula. A0 is what number? The starting amount, which is 500 milligrams. Times 2 to the negative. What's my time? Careful. 7 years is half-life. 20 years. So 20 divided by the 7-year half-life. So when we do this one, we probably are going to have to use parentheses in our power. So this will be 500 times 2 to the power of, and in parentheses, we're going to put parentheses negative 20 divided by 7. It equals 69.005. So basically 69 milligrams is what's left. Does that make sense? I'm going to have you try one like this. So how much is left out of a 1,200 milligram sample with a 12-year half-life after 10 years has passed. So I worded it a little bit different, but it's the same question, same type of question. See if you can plug that into that formula. The amount, sometimes the amount as a function of time is equal to the initial amount times 2 to the power of negative t over the half-life. So give that one a shot, see what you come up with. So we're going to put in the 1200 milligrams times 2 to the power of negative 12 divided by 10. Yep, because the 12 years, oh, sorry, negative 10 divided by 12. Got it the other way around. You are correct. Negative 10 divided by 12. So we have not completed a full half-life, so we know it's going to be more than half. So you sound like, what you have there sounds like it's on the right track. Hunter, do you see how those numbers are going in? This is the initial amount, so that's the 1200 milligrams. T is the time it's passed, so that's 10 years. And of course the half-life is the 12-year half-life.
Total?
12 is the half-life. 1200? Yeah. Yep, that's the total amount. That's the beginning amount. That's the A naught. A0, or sometimes pronounced A naught, is the beginning amount.
Okay.
So we plug this in. We've got 1200 times 2 to the power of, and in parentheses we're going to do negative. Make sure you use that key for negative and not the minus key.
It doesn't make a difference, though, does it? Yeah.
Some calculators will give you an error if you use the minus key instead of the negative key. And in certain situations it'll work, some situations it will not. So 673.48, is that what you had?
Yep.
Perfect. Did it work? Cool. So we're going to look at the current in an RC circuit. The amount of current that flows in an RC circuit. Now, in an RC circuit, you've got your voltage source. You've got a resistor. And you've got your capacitor. Let's say this is a 120 volt voltage source here. Now, we're going DC here just because AC is a little bit more complex to work with. When you... I can't erase that without erasing half the circuit, can I? I'm going to put a switch in here. So when you close that switch, current starts to flow. And at first, assuming there's no charge on that capacitor, the current that is flowing here is equal to the full current, the total current for the circuit. Remember, the maximum current that can flow in that circuit is the voltage divided by the resistance. So you've got the resistance here and you've got a capacitance here. So when there's 0 voltage on that capacitor, that resistor sees the full voltage of the voltage source. As the voltage builds on that capacitor, the resistor is going to see a smaller and smaller amount of the voltage, because the part of the voltage is going to build up on the capacitor, until eventually that capacitor is going to have the same voltage as the voltage source and current stops flowing. So at that point, the resistor is going to see 0 volts. So this is decreasing. It's kind of like a half-life. And when we deal with a circuit like that, we have something called the time constant. The time constant for an RC circuit is R times C, resistance times the capacitance. So let's take this circuit up here. We've got a 120 volt source. Let's say our resistance here is 2.5 kilo ohms. And our capacitance is 400 microfarads. To get up to a millifarad is actually a pretty high capacitance. So let's see, find the current at T equals, what do I want to put in here? Let's say 30 milliseconds. First thing we've got to do is we've got to do some decimal work here. Milliseconds is 0.03 seconds. 2.5 kilo ohms is 2,500 ohms. 400 microfarads. Micro is 10 to the negative 6, or 1 millionth. So we've got to go 1, 2, 3, 4, 5, 6. So it's 0.0004 farads. Now it'll be easier to plug it into our equation, and I have to give the equation next. So the equation is the current that's going to flow as a function of time is equal to that maximum current, so the voltage divided by the resistance, times, remember we talked about the letter E? It's a natural constant. E to the power of negative T divided by R times C. Now as we get further into these circuits, we're going to define something called tau. And tau is a time constant. For a resistor capacitor circuit, an RC circuit, it's R times C. For a inductive circuit, a resistor inductor circuit, an RL circuit, it's R divided by L. And we'll see that when we get heavier into the circuit side of this. So anyway, for now, we're just going to use this formula. So we plug this in. We have 120 volts divided by 2,500 ohms times e to the power of negative 0.03 seconds divided by, here this is going to be 2,500 times 0.0004. So now entering this in the calculator is going to take a little bit of work. So I'm going to start out with this, 120 divided by 2,500. I can just put that in. Times. Now, a lot of you have an E key on your calculator. If you look at it, you have the LN key right here. Usually the E key is a second function above that. So you hit second and then LN. It should bring up an E. Nope. Here, let me come find it for you. E to the X. That's the one you want. Yes. So you've got LN key should go on that top row. Right there. So that's the one you want, is that EX. The double E is scientific notation. That's the one you want, is the second LN. EX. Right. So you hit that second E to the X. And now we have to put the power in there. Now here's one where you do have to use the negative key and make sure you don't use not the subtraction one. So you minus, and in parentheses, I'm going to put parentheses. I could have put parentheses first, it doesn't matter. Maybe you put parentheses and then minus. 0.03 is my time. Divided by, now here I have to put another set of parentheses. 2,500 times 0.0004 for my farads. And be very careful, I gotta put two closed parentheses here. So you look at what I did there for the power. I had parentheses, negative 0.03, divided by, then another set of parentheses, 2,500 times the 4 10,000ths, and I close my parentheses twice.
Did you get 0.04658?
You are correct. So what that is saying is that it's 0.047 amps, or 47 milliamps is what's flowing there. Compare that to the maximum current of the 120 divided by 2,500. 48. So I mean, it's barely decreased. 48 milliamps is what's total, the max current. So it's gone from 48 down to 46.6 basically milliamps. So I'm gonna have you guys try that. So again, our formula, the current is V over R times E to the power of negative T over RC. So I'm going to have you do that for V equals 40 volts, R equals 1.2 kilo ohms, and C is going to be 800 microfarads. Find the current at time t equals 0.05 seconds. So I give you the t in seconds rather than milliseconds that time to make it a little easier on you. So give that one a shot. So I equals 40 over 1200 times e to the negative 0.05 divided by okay, perfect. So let's enter this. So our max current would be 33.3 milliamps times second ln 0.3164. Okay, so something went wrong in your entering there. Let me come take a look. Here, I'll come. Okay, so we seem to have that working. Since we saw that E there, well, how about just something as simple as E to the power of 12? How would you do that on your calculator? Yep. It's just that simple. Now you can see that gets really big pretty fast. That's 162,754.79. I'm not going to write that out. But how about E to the power of 4.23? Perfect. Oops. I didn't hit the second, that's why. You bet. 68.7172. Remember, E is the natural constant. And it developed, it describes the way a lot of things work in nature. And what E actually is it's found by taking 1 plus 1 over n to the power of n as n goes to infinitely large. So the larger number you put in there, the closer you get to E. So if I do second e to the power of 1, that's the actual number E right there, 2.71828, right? If I use this expression, though, if I do 1 plus 1 divided by, and let's put in 1 million. Notice I get really close to it. It's off after about 4 or 5 decimal places. So that's where that number comes from. But what it is things in nature that do exponential growth and decay, that E tends to describe their growth and decay. So we saw it with the electronic circuit, capacitive circuit. It also works for population growth. They used to do something called continuously compounding interest. When we did compound interest, we just did it every quarter or every month. anything that is continuously compounding, like population growth or growth of bacterial colonies, stuff like that, you can use E to describe its growth. Or its continuous decay as well would be the same thing. We'll look at decay of a capacitor or an inductor. Same type of thing is going to happen. How if I give you something like 5 to the power of pi? Safest in that case, probably use your pi key. Like 156.99. Okay. Did you guys get a chance to do much in the packet that we assigned you on Thursday? Okay. I gave you mostly page 469. Which was solving these equations, solving these problems with the numbers they gave you. And they go through examples of voltage and stuff like that. They're looking at voltage across a capacitor as it charges or discharges. You know, we looked at current, so it had a little extra key in there. If you're looking at an RC circuit and you want to look at the voltage in the capacitor, voltage is a function of time is equal to your voltage. V0 is your voltage input to the power times E. This is actually describing the discharge of the voltage on that capacitor as the voltage slowly discharges back out. So let's say you've got a capacitor that is charged to 80 volts. The resistor is 2 kilo ohms. The capacitor, let's go 1 millifarad. And let's find VT. Well, I'm gonna do a little bit of a notation thing with you here. So I'm V and then the 0.06 seconds in there. That's find the voltage at 0.06 seconds. So that's for T equals 0.06 seconds is what that means. So it's just a little bit of a notation. So I'm just going to plug it into the formula here. My initial voltage is the 80 volts that it was charged to, times e to the negative t. Well, t is going to be the 0.06 divided by, and in parentheses, 2 kilo ohms is 2,000 ohms times 1 millifarad is 0.001 farad. And make sure you have 2 close parentheses on it. That sounds about right. You get the same thing, Hunter? $77.6356. So you've lost about 2.36, 2.37 volts in that 6 milliseconds. Don't forget the negative again in there. Filter clogged on the one up there. So it'll run for about 5 or 6 seconds and shut down. What's that? Perfect. Perfect. This one's much brighter and better anyway. I like this one. They said they're just going to take that one down and put a new one up, and then they'll take that one and clean it and everything. Hopefully they just put this one up there because I like this one. Brighter colors. Well, I was tempted to just take that one down and put this one up there myself. It's not that hard to do. I don't have a ladder. I'm not going to stand. If I stand on the table and the table tips over and I get hurt, they're going to really be pissed at me. Yeah. So in that packet,
Stand on the swivel chair.
Yeah, stand on this higher swivel chair. That's
Yeah.
one of the old instructors for your program used to go around, because on your ladders, you know, even the second step from the top says not a step right on it.
Yeah.
And he used to go around, he would scream it, because I mean, especially when you're up in the ceiling working on stuff, some guys would stand right on the very top of it, which he'd really get pissed. But you know, just getting up on that second one from the top, he'd really get on their case. Like, this is not a step. And there's a good point to it, because in industry, if you are doing something that the equipment says it can't do and you get hurt, they will deny your workers' comp. No, you are misusing equipment. So on that packet, page 469, 1 through 25, again, I'll have you keep working on those. And I am going to send a quiz home with you to bring back in tomorrow.
Are we supposed to graph?
Do some of them say to graph?
Then 1 through 20 graph.
Yeah, I don't try to graph them. Just, well, you know, for the first couple, it wouldn't be a bad, yes. Let's do this. Let's just have you do like 1 through 9 there to graph, and then skip up to 21. So let's have you do 1 through 9 and then 21 through 25, because that's a lot of graphing. But like for number 1, let's do that together right now quick. Y equals 3 to the x. We know we don't have to go negative. From x equals -2 to +3. Well, if x is -2, 3 to the power of -2, and I'm going to make this a little bit larger scale here. If x is -2, 3 to the power of -2 is 1/9. So that's right in here. I'm going to change colors. That's right in here. If x is -1, 3 to the -1 is 1/3. So that's going to be right here. What I'm doing is I'm making a table here, but I'm not writing it out. If x is 0, 3 to the power of 0 is 1. If x is 1, 3 to the power of 1 is 3. So that's there. If x is 2, 3 to the power of 2 is 9. That'd be way up here off my graph, so I'm not going to put that point on there. And if 3 to the power of 3 would be 27. So x is 3, 3 to the power of 3 is 27. So I get that graph. Looks like that. Makes sense? So then there's going to be ones that are a little bit different, like 7 is 1.5 to the -x. That's going to go this way. It's the -x. It's going to be backwards. So yeah, I do want you to graph at least that 1 through 9. Okay, let me pass out the, so it'll be that page 469 and those problems there. Then I'll pass out the quiz for you quick. So you take a look at that, see if you have any questions before you have to get out of here.
So you feeling better from yesterday?
What's that?
Feeling better from yesterday?
Yeah, I'm feeling better. Oops, sorry. Yeah, sorry the message didn't get to you guys. I should have came down and just told Bart that I was leaving. That way, no one would have got through.
No, it's kind of funny. Actually, when I walked in, I thought you were gone again. You recognized me with the haircut.
Oh, sure.
And I thought you had gotten a sub or somebody.
Oh, unless I'm like planning on being gone for something, they almost never get a sub for me here.
Okay.
Probably because it's difficult to find anybody that really kind of understands the material. Just to give you a heads up then, tomorrow we're going to talk about logarithms, which is going the opposite direction from the exponentials. Thursday, I'm hoping to have the Woods guys doing a quiz. So we can talk about resistor capacitor and resistor inductor circuits. Which would open us up to next Monday doing a quiz, depending on how that goes on Thursday. A lot of times we have to take an extra day to go back over that stuff again. So for you, if you're thinking about Mondays, depending on how things go Thursday, it'll give you an idea of what's going on Monday. So the same stuff we're discussing Thursday, we'll probably be going over. Either we'll be going over it again on Monday or taking a quiz on it on Monday. I would say probably very small chance that we'll be ready for a quiz yet Monday.
I won't be told after spring break.
Oh, you'll start that? Okay. Gotcha. Just remind me then when we get to that point.